Okay, here's a very standard application of differentials, and that is this notion of measurement versus calculation, right? So, for example, if I want to measure, if I want to find the volume of a cube, what would I do? Well, I would measure one side of the cube, and then calculate the volume by taking that side and cubing it. Right. So if I want to calculate the area of a square, what would I do? Well, I would measure one side of the square, and then to calculate the volume, I would square it. So here's the real world application, right? Measurement is not 100% accurate no matter what instrument you are using to measure. You're always going to be off just a little bit. So the question is, right, what will my error in measurement cause for the error in the calculation, right? So I measure the side and then I feed it through the calculation formula. What's that gonna, right? How bad is the error gonna blow up when I feed it through the formula or whatever? So here's an example of that. So we've got the radius of a spherical ball bearing is measured and observed to be 21 centimeters. And the thing that we use to measure this ball bearing, we know that that instrument is only accurate to within 0.05 centimeters. So we're guaranteed that the measurement of the radius is going to be either 21 plus 0.05 or 21 minus 0.05. So not 25, but it's going to be somewhere in that window, right? Minus 0.05 plus 0.05. So the radius is actually somewhere in the window, right? So we want to estimate the error using the radius to calculate the volume. So we measure the radius to be 21 centimeters. We plug that into the formula for volume. And now how off are we going to be when we get that return data, right? So you plug 21 into the formula for volume, it's going to spit out some number. How accurate is that number going to be, that the output that we get from the formula, right? So that's part B, right? What is the error that we might get in calculating the volume, and then how bad is that? So we'll have to say what we mean by how bad is the error in part A. So we'll deal with that when we get here to part B. We've measured the radius of a ball bearing and we got 21 centimeters, but we know that our measurement, that measurement of 21 is going to be off by plus or minus 0.05 centimeters, right? Because measuring instruments aren't 100% accurate. So here's the curve for volume if we know what the radius is, right? So this is the thing that we measured. This is the thing that we want to calculate, right? So the x and the y. So if we look at the radius axis, right? So the x-axis, right? We've measured our radius to be 21, but we know that the radius might be as little as 20.95. We know it might be as large as 21.05, right? So when I plug this lower end radius measurement possibility into the function, right, into the volume function, I'm going to get, you know, the actual volume minus some error, right? So here's the actual volume. When I plug 21 into this thing, whatever that turns out to be, we'll check what it is later. But here's the target, right? The volume might be this little, or it might be, right, on the other end of the spectrum, it might be this much. So really what we're trying to do is approximate how far, right, how much the error is on either side of the actual target volume. So instead of using the function, we're going to use the tangent line at the point 21 in order to do that. So here's that picture, right? Here's the same curve, 4/3 pi r cubed, right? And now draw the tangent line at 21. And so instead of looking at delta V in moving from here to here. So a change in R will cause a change in the volume. Let's approximate that change in the volume using dV instead of delta V. So now, what's dV? Well, we use this tangent line here, and we can see that the tangent line is going to give this change in volume dV, which is an approximation to, right, the actual change in volume from here to here. So this is, you know, when we're really close to 21, this will be good enough. And then on the other end, right, I'll use the line to find the change in volume, but these two numbers are going to be the same. So instead of getting this sort of asymmetric window about the target, right, this one's smaller than this one, these two things are going to be the same anyway, because we're using a line, right, to measure. So all we need to do is just compute dV instead of delta V, right? And we know how to compute dV, right? That's just, dV is just V prime of the tangent point times delta R, or delta X. In this case, our change in radius is 0.05, right? So the derivative of V is just bring the 3 down in front, so I get 4 pi R squared. So I get 4 pi, the radius squared, times delta R, and that's roughly 277 cubic centimeters. So let's think about what that says for a minute. It says if I'm off by just 0.05 centimeters, that's going to cause my volume to be off by 277 cubic centimeters, right? That seems terrible. That seems like, wow, you know, we really need to find better instruments to measure these things, right? Because being off by 0.05, that doesn't seem terrible. But then we get this volume that's off by 277 cubic centimeters. Is that good or bad? So we really need a way to see, you know, how terrible, or is this okay? Is this terrible or is this okay? So now we want to introduce this concept of relative error in order to assign some measurement of how good or bad this approximation is. Okay, so how bad was this error that we got in the calculated volume? Did we hit the panic button too soon? Turns out the answer is no. It turns out that a 0.05 error in the measurement of the radius causing a 277 centimeter error in the volume is not so bad. And here's how we can tell. So again, off by 0.05 centimeters in the radius caused us to be off by 277 cubic centimeters in volume. Now the target volume, right, that we got from our target radius of 21, that was our measured radius, right? So I plugged that into the formula for volume and I got 4/3 pi 21 cubed. The actual volume then is about 38,792 centimeters cubed. So really, right, to be off by only 277 cubic centimeters relative to 38,792, now that doesn't seem so bad. So now we want to talk about relative error, right? So, you know, it's the little change in y compared to the actual value in y. So the little change in the volume compared to the actual volume is not so bad. So let's try to quantify that, right? The relative error, it's the little change in the volume divided by the actual volume. So now we get a ratio, and so this ratio is just 0.00714. So in terms of a percentage, that's 0.7%, right? That's not that bad, right? So 0.714% is really how bad the error actually was, right? So not that much. And so here's another way to view this, right? to be off by 0.05 centimeters away from the target measurement of 21 centimeters, how bad is that? Well, to be off by 0.05 centimeters compared to 21 centimeters, right, that's just 0.238%. So 0.2% is the relative error in the measurement of the radius. And now that's going to cause a 0.714% relative error in the calculation of the volume. So really, that's not the end of the world. That relative error is not so bad. This ball bearing of radius 21 centimeters, let's say that's the target radius. So let's say we know what that thing is. So now the question is, how accurate must the measuring device be to guarantee that the relative error in the calculation of the volume, right, using the same 21 centimeter radius measurement, is less than 0.5%? So now, right, now we need to know, now you've handed me how close I have to get in my calculation of volume. And so that's going to determine how accurate this measuring device better be, right? Now I'm on the job. And the boss says, you know, you've got to compute the volume of this thing, and you better not be off by more than 0.5%. So I better find some calipers that I know are going to be off by how much, right? So we need to find, right, how good does this measuring device have to be to guarantee this this calculation of volume is less than 0.5%. So we saw that the first measuring device we used, that was that allowed an error of 0.05 centimeters, right, in the measurement of the radius. That's not going to be okay in this case, right, because we saw that when we were off by 0.05 centimeters, that caused us to be off in our calculation of the volume by 0.714%. And that's bigger than 0.5%, right? So that measurement was 0.238%. So this new instrument that we use, it better be more accurate than being off by 0.238%, right? The percentage has got to be less than that in order to guarantee that our calculation of volume is going to be smaller than 0.5%. So how are we going to do this? Well, much like the same thing we've been doing with all these other inequalities, we'll set up some inequality and we'll solve and see what happens. So what do I need to have happen, right? The goal is to make my relative error less than 0.5%. So 0.5% written as a decimal, 0.005. That's the goal. So what's dV and what's V? Well, dV is V prime of R times delta R, right? That's the formula for the differential. So V prime is just the derivative of 4/3 pi R cubed. And so that's going to be 4 pi R squared times delta R over V itself. So that's 4/3 pi R cubed. So I need that thing to be less than 5/1000. I'm going to use fractions because that helps me see what's going on a little better. So now I'm going to just solve for delta R over R. That's going to give me the relative error of the radius, right? It's d the thing over the thing is the relative error of the thing, right? So I'm going to solve this thing for delta R over R. So you know, the pi's will cancel, the r squared up here will cancel with 2 of the r's down here, so I'm left with an r in the denominator, right? 4 over 4/3, that's the same thing as flipping 4/3 and multiplying by the top. So there I'm going to get 3. This is really 1 over 200, and so to divide by 3 is going to give me 1 over 600. So just do a little algebra to get from here to here and simplifying all the terms, right? So now delta R over R is less than 1 over 600. What does that tell me? At this point, I know that my relative error in the measurement of the radius cannot be any more than 1/6 of 1%, right? And so now let's see what this amounts to in terms of the centimeter window that I'm allowed, right? So remember, the target was 21. How much am I allowed to be off, like plus or minus X number of centimeters? How many centimeters am I allowed to be off? So, right, delta R over R, that's the change in the R, so how much I'm allowed to be off over the measured radius, which is 21, that needs to be less than 1 over 600. So what's delta R? That's what I'm looking for then. So we could, I mean, if we were asked about the relative error in the measurement of the radius, we would stop here. How many centimeters are we allowed to be off? Well, we have to keep going a little bit. So there we would need to solve for delta R. So just multiply both sides by 21, run that fraction through a calculator. That says that delta R has to be less than 0.035 centimeters. And so that's the allowable change in the measurement of the radius that I'm allowed, right? I can be off by 0.035 centimeters. So the accuracy of the measuring instrument, right, I'm allowed to be a little bit more than 0.035 or a little bit less than, right? So that's the window, if you like. So here we've got 21, and then I can be off by as much as 21.035 centimeters, or 21 minus 0.035, whatever that turns out to be. I'm not going to try to do that in my head. So this would be a good final answer if we want to know, right, how many centimeters, give or take, are we allowed to be off by.